recording started. And the doorbell rang just as I said that. Okay, I'm just not going to say that. I'm just going to start class. How's that sound? First order of business is that you all should have had the chance, if you've checked your email since maybe yesterday, not early this morning, download your feedback for homework 1. If you did not get all 8 points, then you have the chance to revise and answer whatever else I needed to know and send it back to me as a revision. If you have all 8 points, you don't need to do anything. So I inserted a lot of commentary in your drafts with respect to sort of, by the way, blah, blah, blah. There's nothing you need to do in response to that. But it did bring up a number of interesting things that I thought would maybe be good to go over as a group with respect to what people have described in previous literature. So there were a number of folks who reported that the article they read said they did exploratory factor analysis, but they used principal components extraction with a Varimax rotation or something. So that's not exploratory factor analysis, that's principal components analysis. And they are often sort of shoved together into the same set of software options, which is, I think, why they tend to be confused. But principal components is conceptually backwards. It is a model in which the arrows go from the responses as predictors into a component as an outcome. So the goal of principal components is different than what it is in factor analysis. The goal of principal components is to reduce the amount of information into fewer variables. So where that tends to be used still in practice is in neuropsychological data. And I'm going to embarrass myself with my lack of vocabulary, but like voxels and stuff, like when you have all the electrodes and all the different places, like they collect tons and tons of information. They tend to use PCA to summarize that information and so that they can reduce the amount of variables to be analyzed. PCA in terms of scale development has a long history, but it doesn't really make sense because it's not predicated on the idea of finding commonality. That's not what it's for. So for those of you who have articles where that's all they've done, that's actually good news for you because that means you have a lot of things that could be done and make a novel contribution in terms of the development of whatever scales or items. Another thing that I wanted to point out is that in validity evidence, a lot of times, even after they fit a confirmatory factor model or something like that, folks will compute sum scores and then correlate the sum scores as evidence of validity. Every time you make a sum score, you are actually fitting a measurement model without realizing it. A sum score is a unidimensional measurement model where all of the loadings are the same and all of the error variances are the same. That is the only situation in which you would come to the same conclusion by estimating a latent factor as calculating a sum score. So one of the things that we'll do towards the end of this handout is actually teach you how to test those assumptions, whether constraining all of your loadings to be equal, saying that all of the items are equally discriminating. We can see whether that's supported in the data, as well as equal error variances. Does anyone have any questions after looking at my feedback or looking at the article as to things that would be useful to discuss as a group? Zoomers, looking at you. Roomers, one question?
Can you briefly go over partial correlation?
Partial correlation is the relationship between two things sucking out a third thing. Okay. How's that? As opposed to semi-partial, which is controlling the x's and not the y. It's not really a thing anymore, I would say. It's one of those things that people did before they could do other stuff that's cooler now. Another thing that a common theme is that a lot of folks had scales that have lots of dimensions. For the purposes of this class, you only need to pick one if it has at least 6 items. If it has fewer than that, then maybe pick 2 or 3. If you want to do more work than I am requiring, that is okay, but just be prepared that it's more work. If it would be useful to you to, say, analyze 3 different traits and get my feedback on it because you intend to publish this, great. But otherwise, you don't need to go to that length because I want to make it fair across people, and some people have much more complicated sets of items that they're trying to work with. With respect to how the traits relate to each other, a number of you reported that you were supposed to have a higher order factor. So for instance, in the example that we're working through, forgiveness scale has, by the way, just got another request this morning. Attention, Internet. You have my permission to use the forgiveness scale. Seriously, it's fine. It's publicly available. Go nuts. Check out the Heartland Forgiveness Scale website, which you can find if you Google those 3 words for all of the information about it and its many translations into other languages. It's still fine. Forgiveness is supposed to be one overarching individual difference characteristic that has 3 facets or 3 subdimensions. So forgiveness of yourself as one of those, forgiveness of other people, and forgiveness of situations, which is the set of items that we're playing with. So if you only have 3 lower order factors, the same rules apply with respect to identifying that higher order factor as if you only had 3 items. It is literally the same. It's just at a higher level of the model. So there is no way that I can test formally whether a single higher order factor fits my 3 lower order ones, because it has to. I have 3 covariances among my 3 dimensions of forgiveness, and I can represent those 3 covariances equivalently with 3 factor loadings onto a higher order factor. It's the same. That is unit 8, by the way. So we will get to that. But I wanted to foreshadow that. If it's a higher order factor that is part of your scale situation, you can ignore it for now. Just pick the lower order ones to focus on because we're working on measurement models for the time being. Okay, questions or comments? All right, so then should we talk about formative assessment number 2? This went really well. I only have nitpicky things to say, nitpicky clarifications, but everybody seems to have the big picture as well as the notation down, or at least you were able to find the right answers in the slides, whichever it is right now. Working towards independence, but if you need a little bit of review, that's totally fine. That's what this is for. So the 3 kinds of item or indicator parameters, and I asked for a definition of each, which some folks did not do, but that was the idea, is to know what they mean. So let's do, what's one of them?
Factor loading.
Factor loading. What's the symbol that I use for that? Lambda. Give me a synonym for factor loading. Slope. Give me another synonym.
Discrimination.
Discrimination parameter. Yeah. What does it tell us?
The expected change in my item score for 1 unit change in factor score.
Yep. Expected difference in the item response for a 1 unit change in the factor. Yes, indeed. What's another item parameter? Intercept, yes. And what's the symbol for that? Mu, or fancy U, someone wrote down. I like that one. The U with like a line in the front of it. I don't really care what symbols you use as long as you're internally consistent in your notation scheme. But yes, what does an intercept tell us? Not quite. I need another word in front of it if you're going to use the word mean.
The expected.
Yeah, conditional or expected. Because it's the mean for what kind of person?
Factor 0.
Yeah, someone with a factor score of 0, which usually means the average of the trait, given how we scale factors, which is the next question. So yeah, I don't want you thinking that item intercepts are always means, because that won't always be true. They are conditional on a factor score of 0. And both of those are fixed effects, meaning each item gets its own, and we don't say anything about the other items. It's like this is this item's intercept and this item's slope, the end. As opposed to, what's the third one? And this is where I got to get nitpicky.
Error variance.
Error variance. So several of you wrote down that E is the third parameter, and that is true if you're looking at the equation, but that's not what's being estimated. It's the variance of the E's that is the parameter. Because on your output, you don't get an E for each item, because it would have to be for each person for each item. So it's the variance across people in the E's per item. That's the parameter. So errors are random variables is another way of saying it. And I don't want to say random effect because that will be confusing, but I'll say random variable because it's a variance that we care about. And that is true just going back to any linear model. E is never a parameter directly. It's always a variance. Okay, so that went well, I think. Any questions on that or things you want to clarify? All right, structural parameters then. How many are there? 3? Feel free to read from the screen, yeah. What are they?
Factor means variance and covariance.
Yeah, factor things. So measurement model is item things. Structural model is factor things. Factor variance, factor mean, factor covariance. Which ones of those have to have some kind of scale put onto it by us?
Variance and mean.
Yep, mean and variance is indeed. A few folks forgot about the means and just talked about the variance. We can't forget the mean side. So how then do we give each factor of variance? What are my choices?
Fix different things.
Fix different things, yes. Something got to be 1 is the way I would say it.
The variance or the factor loading with your marker item.
Yes, so either the factor of variance or a single loading for one of the items that that factor measures is fixed to 1 by tradition. Could it be 10 instead?
Yes.
Sure. Could it be 0 instead?
No.
No. Could I have what happens if I have a variance of 0? It's a constant, not a variable. Whole thing's going to break. So I make that because I see that mistake at least once every time I teach this class, that someone switches where the 1s and 0s are in their code and the model won't run. So yes, doesn't work. So either the factor variance is fixed to a constant, usually 1, or one of the loadings is fixed to a constant, usually 1. What happens if I do both? Will the model run? But what am I saying then? It will run, you're right. If I fix the factor variance to 1 and I fix the loading to 1, Zoomers have it, yes, it would be perfect. That item is perfect. All of its variance goes up to the factor, nothing left over for not the factor. Could that happen? Sure. Is that likely? No. So that's the factor variance side. The other side then, what are my 2 choices with respect to scaling the factor mean?
The factor mean to 0 or the item intercept to 0?
Yeah, one of the item intercepts, usually it would be in correspondence with whichever item has the loading fixed to 1, but it doesn't have to be. So the intercept is fixed to 0 or the factor mean is fixed to 0. Which is more common?
Factor mean equals
Factor mean, yeah, that's the default in all the packages. Factor means are fixed to 0 unless you specify otherwise. Could you pick 10 instead? Or 1 or 12?
I would say.
Sure, just something, right? Plant your flag, pick your key, find the center of your formation, whatever analogy you want to do. It's up to you. Those of you who are learning Bayesian psychometric models, I will warn you, I have seen several papers where I look into the code and their model's not actually identified. Like, they don't have these constraints in there. And I remember asking Jonathan about that, like, how does this not break? And he's like, well, So the magic of Bayes, maybe it won't break, but I have to think that it makes the estimation more troublesome than it needs to be. So especially when we get into the world of IRT, some of these things might still work with they're not constrained, but you might get garbage numbers out of it. So this idea that each imaginary variable needs a scale is constant across all types of models that you would fit for different types of responses. What about the factor covariance? Do we need to like make up a number for that if there's more than one factor? What do you think? Yeah, we just let it be estimated. Now, could we force it to be 0?
Probably.
We could. That would be a strong statement that these two things are unrelated to each other. And most of the time, if you're putting multiple factors into a model, it's because they're facets of the same thing. Like, you wouldn't usually bother to put them together unless they were parts of something that you conceptualized as related. By the way, the idea of constraining a covariance between factors to 0 is the same thing as an orthogonal rotation in EFA or PCA, like Verimax, is an orthogonal rotation. And it makes little sense in most cases when the whole point is to see which items load on factors because they all kind of measure the same area in terms of a construct. What happens if I constrain a factor correlation to 1? Can I do that?
Yeah.
Could do that. That's like saying I have one factor. So the test of whether you need 2 factors versus 1, another way to think about it is a 1-factor model has a correlation that's perfect between the two, allowing it to be something less than perfect could make the model fit better, in which case 2 factors is better than 1. So that covariance between factors then is a way that you can put constraints in terms of the dimensionality. All right, I think that's the end of that question. Any other comments or questions about that? Good so far? I think it's good. So far, so good. Degrees of freedom. So first, how are they calculated? What goes into degrees of freedom in this context?
Means, variance, and covariances.
Yep, the number across items means their variances and covariances. There's a formula for that. N times n plus 1 over 2 plus n, or whatever symbol I used. That's n, and sorry, n was an hour ago, and now it's v. So, whatever. This is the 2 classes are merging together in my head because I am talking about the same thing with 2 different sets of vocabulary. I really am. So the end of example 4 in this class and the end of example 5 in the longitudinal class, we have the crossover between the 2 that we haven't gotten to yet, but I plan to go over it at some point. So degrees of freedom then pertains to the amount of information in the variance covariance matrix and means for your indicators. And then what do we need to know if we have enough to fit our model? How many things would we estimate? How do we count those up? If I have 5 items, and I think they measure one thing, how many parameters does it take to say that? Let's count them up. How many intercepts?
5.
How many error variances?
5.
How many factor loadings? So I'm at 15. Do I need to count anything else? If it's 1 factor? What if it's 2 factors? We add the covariances. What if it's 3? I don't know if we have enough information to do that. Because at that point, like, you would have to have 1 factor be identified by just 1 item, and that won't work. You would have to say that it has no error variance because you have no way to estimate it. So yeah, so then degrees of freedom for the model is the difference. How many more parameters could we add is how many degrees of freedom are left over. And so then the labels. Under-identified refers to what kind of degrees of freedom, numerically? Not enough. Otherwise known as negative. When you're trying to estimate more parameters than you have pieces of information going in, how many degrees of freedom make the model just identified?
0.
0. And then over-identified?
More than 0.
More than 0. Positive, yeah. What do you need to make your model even go, like estimable? How many items per factor?
3.
Just 3, if that's all you've got. How many to make it estimable and testable? 4. What if you only have 2? Yeah, constrain the loadings to be equal. So this set of 2 versus 3 versus 4, this is if that's all that's in the model. If you have 2 indicators each for 2 factors, so 4 items altogether, is that okay? Or it could be okay depending on something.
Could be okay if they have a code.
Yeah, they have to have, the factors have to have a covariance in that case. Yep. So if I have 2 indicators each of 2 factors, as long as there is a covariance between factors, then you're good. But if not, then it's 2 and 2, and it's like each is by itself, each is under-identified. So those of you who have scales that are only only 3 or 4 items each per factor, I'm asking you to fit 2 at once so that you have enough degrees of freedom to actually have the chance to be wrong. Because that's essentially what you're saying, is when your model is over-identified and you have parameters left over, you have room to be wrong, and that makes it testable. The more degrees of freedom you have, the more room you have to be wrong. Okay. I think that's the last question. Yeah. Any questions on that question or otherwise? Okay. So yeah, like I said, only nitpicky comments on some of that. Otherwise, it's all good. Trying to think if there's anything else that came to me as I was reading these today. I don't think so. I think we're good. What do you have to do for next week? Nothing! Yay! Other than, you know, read the 8,000 articles on your reading list, go back over the material and that kind of stuff. No, nothing's due on Monday of next week, and I will let you know when homework 2 is available. What that will be is using the homework system to fit CFAs on canned data, where I will have the correct answers available and you will get immediate feedback. There's no results section, but there will be multiple choice questions about various issues of this type of stuff, and model comparisons and things like that. All right. Let's see here. Last time we were talking about what? So I have this up to jog our memories. What do you remember from last week? It's been 5 days. I think that's a valid question.
You left us on a cliffhanger.
Oh, I did, didn't I?
Yeah.
What was the cliffhanger?
Your model was significant, so that's bad.
Yes, it is bad. So we talked about global model fit. Should we review that a little bit? How we know if something is good or bad? So let's go back several pages then to where this is, let's see, this one. I'm on page 8 of example 4, where we were looking at the fit of a single factor model like it was supposed to be. I have 6 items that all in theory measure forgiveness of situations. So 18 is the number of free parameters in my single factor model because I have 6 items times 3 parameters apiece. And let's see, HO of negative 11,000 in some, is that good or bad? Trick question. I don't know yet. Doesn't mean anything. It only has meaning relative to some other model. So yeah, and so in the solution, thank you for reminding me we should probably look at that. In the solution, let's go to the standardized solution because that's the easiest to work with. Here it is. Standardized solution was on page 4. We have the standardized factor loadings that are in the scale of Pearson correlation. That's what they represent. And it looks like the items that were reverse coded are loading relatively higher. So they represent more of what this latent factor is according to this solution, but they all contribute to some extent. So is one factor good enough? That's what we need to look at for the global fit. So HO versus H1. That's the idea of how much worse than perfect is my model, or perfect is H1. Perfect is the saturated model where we just estimate what the means, variances, and covariances want to be and figure out how tall that makes the data, where tall is log likelihood. Now, do I need to do the likelihood ratio test to compare these two log likelihood values? Do I need to do that, or is it done for me? It's done for me. Every package on Earth does it for you. This one it does for you. That's what the chi-square test of model fit is. It is a rescaled log likelihood. So it's the difference in log likelihood after correcting for these scaling factors which indicate deviations from multivariate normality. And significance is bad because we are significantly worse than perfect. Other fit indices, RMSEA is also relative to the perfect model, so the best it can be is 0. Conventionally, we want RMSEA to be 0.05 or less, maybe up to 0.08, but not above that. Ours is 0.17, so definitely not good enough. RMSEA also comes with another hypothesis test, cough, cough, homework question, a test of close fit, which is whether it's less than 0.05. And here our p-value is 0 to 3 digits saying nope, 0.17 is decidedly not less than 0.05. So we're not only worse than perfect, we're worse than close. Not good enough, point being. SRMR, which is on the top of the next page, is also another one that's relative to perfect. So the smallest it can be is 0. And this one is how far off, on average, are the correlations between the perfect model and your model. So like what this is saying is that on average, the model predicted correlation from my single factor model is off by 0.086. And this is another one where I don't know, people make up different numbers. 0.05, 6, 7, 8, somewhere in there is good enough. So this one's more optimistic than the others. One of the differences is that RMSEA takes into account the number of parameters spent. So it will get less happy with you when you add stuff to make it fit better. The other two, so these are relative to a different baseline. These go by different names. CFI, TLI is also called NNFI, and it might be called adjusted GFI or something close to that in other packages. These ones have a different baseline. It's the null model. Do you remember that one? Null says what? No covariance. It lets the means be there. It lets the variances be there. This is no covariance.
Is that compound symmetry?
Not even compound symmetry. It is
BC?
BC, diagonal. Yeah. But it still has the means. So it's not directly analogous. And actually, for those of you who would use structural equation modeling to fit growth models, this isn't the right null model for that, because it has all the means and variances perfect, and that would be part of what the growth model would be trying to recreate. So this null model is only appropriate for in a measurement model context. But these numbers, the best they can be for CFI is 1. TLI can go above 1 because it doesn't have a boundary on it. But this says how much better than the worst model do you have? So these you want to be greater than 0.9 or 0.95. And last but not least, do we care about this one, chi-square test of the baseline model? No. Just ignore it. It has nothing to do with your model. It's comparing saturated versus null. It answers the question, is there anything worth modeling here? Yes, if it's significant. Here's the same stuff in R. It's all the same numbers, just rearranged. So you'll have to do a little bit of searching to find the right stuff. It adds some extra versions of fit indices that are not in M+, which means I'm not going to ask you about those in homework. But otherwise, exact same values and exact same conclusions. All right. So the model doesn't fit. So what do I do next? Pack up and go home? Yeah, sorry, it's only 2:30, not time yet. Tell NIH that I can't go any further because my factor structure wasn't confirmed, sorry. No, not cool. I got to figure out why it doesn't fit. And even if those fit indices were acceptable, I would still go through this next step, because on average things work is not the same thing as it works for every single part of your covariance matrix. You could have one part that's seriously wrong, but if everything else is good, it could wash out. So local misfit is what we would examine, and that is the discrepancy between what the model says and what the data say for every single piece of information we're trying to recreate. So that's where I'm on page 11. Nope, 12. That's where I'm at here. So in M+, if you search for the term residual in the output, you will see all of these tables show up. I asked for them via certain functions in R. These are from R because they take up less space. So we have the model implied covariance matrix from the single factor model, as well as the model implied means. And then I have over here in a box, which works for this handout, unlike my previous class where the boxes are all misaligned. This is from the saturated model. And so the difference between every single spot in here, that difference is local misfit. And it's presented in 3 different scales. So the notation is in covariances in M+, or what R calls raw. So This is a residual covariance matrix is what it's called, but it's not the residual ease. It is discrepancy. It's unfortunate that the same word means multiple things. But these are offnesses. Oh, this is the thing. I fixed this discrepancies last time, and I forgot to save it. Discrepancies. You know. Double check if this is correct. Quite certain it is not, but thank you. So these are discrepancies, and we don't have any discrepancies on the diagonal, which means what? Our variances are recreated. They have to be, because we allowed each item to have its own error to soak up whatever the difference needed to be to get back to the right total. Likewise, the discrepancies for the means are 0 because we allowed each item to have its own intercept. Where the misfit comes in is inside the covariances. Because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 covariances that are trying to be recreated from what? The loadings. And how many of those do we have? I got 6 items. 6. Yep. So 6 items, 6 loadings to recreate 15 covariances. That's where the 9 degrees of freedom for the model come from. That's it. So the first table is in covariance form, which is less helpful because it's like, is that a lot? It depends on the scale of the data. So then you could put them into correlations, which is more helpful. So the biggest offnesses, for instance, are between 2 and 4. They have a positive residual correlation, meaning they are more related in the data than what the model says. Here's a sizable one in the opposite direction. Items 1 and 2 are less related in the data than what the model says. And then one more scale for these, normalized residuals, and this is the keyword you would search for in the output to find it, is these are like z-scores. So it's the discrepancy in the covariance divided by the standard error of the covariance in the observed data. So you can interpret these as more is worse in absolute value. There's no hard and fast rule as to how big they have to be because it depends on the size of your, it depends on the number of people. Because larger data sets will have smaller standard errors and make these things become larger values. So what I would look for in practice is relatively large values that stand out. And I've highlighted them. So yeah, the positively worded items all have more relationships in the data than what the model says. The negatively worded items, that is true for to some extent, but they're not as big of a problem because they had more of the loadings. So the factor itself is already representing more of the negative items. So there's less left over to be incorrect. All right. This sounding familiar? No. So if you only have one factor, then there is no difference between EFA and CFA. If you have multiple factors, then what EFA does is allow loadings on every single one of them for every single item. So then you have to figure out what each factor means based on the loadings. And that's where, well, I think it's this, and I think it's this. You're both right. It's dissatisfying.
So this is like you're specifying the factor and then you're seeing what the covariances are, where with EFA it's the other way around?
In theory, you could do this for both, but in EFA, you don't know what the factor means.
Okay.
You have to figure that out post hoc via looking at the loadings and then choosing a rotation that you like the best in terms of how it works, where there's no standard for what, because rotations all fit equivalently, so there's no mathematical basis for preferring one over the other. These are discrepancies, is the way to think about these. These are the reason why the sum of this is why the model doesn't fit. So this is our key to figuring out how to make the model better. And there's one more thing that you can look at that is going to take this information and distill it down into advice. Remember talking about these? Modification indices, otherwise known as cheat codes, where they're like, hey, I know how to fix this. I'm just going to let the part of situation items 2 and 4 that's not the factor be related. And then the model will perfectly recreate that covariance because that additional error covariance is going to fill in the hole and resolve the discrepancy. And it's going to suggest I do the same here, and it's going to suggest I do the same here, and it suggests I do the same here with a negative error correlation. So all of these suggestions from the modification indices are with statements. In M+ language, with means covariance. So item 2 with item 1 is saying, let the part of the item that is not the factor have a relationship. And these are called residual covariances, not to be confused with this table, which is residuals for covariance. I know. I didn't make up the words. I would have chosen different ones. This is where it's confusing. So I'm trying to think about these as discrepancies and avoid the word residual, because these extra relationships that it's suggesting are residual covariances. So the way that you would read this table is MI is by how much would your chi-square go down if you put this in your model. And all of these would change if you implemented one of these suggestions. They are not independent, absolutely. Yeah.
In this case, the chi-square is equal to log likelihood?
The chi-square is the difference in log likelihood between the perfect model and your model, but it's rescaled for the correction factors. So there's another layer to the calculation, but conceptually it's the same idea.
Okay.
So our chi-square was like 309. So this would be like, hey, if you let items 1 and 3 be related, your chi-square would go down by 143. And if you let items 2 and 4 be related, it would go down by 161.
I have a clarification here. You said that it's not independent of, like, if we made all these changes, these numbers wouldn't all fluctuate. But, like, making that change, and only that change, that's the 161
Yes.
is how it would change.
Yeah. Yes.
Okay.
That's the prediction for that change. But as soon as you implement that change, that would adjust the entire prediction of everything. Yep.
But it's not saying if you made all of these changes.
Mm-mm.
Okay,
It's per line.
great. Thank you.
Sure. And so then the expected parameter change is the next column. That's in the unstandardized solution. And then in the standardized solution is over here. So for instance, if I did this suggestion, which would result in the biggest change, then what I could expect is that the errors for items 2 and 4 would have a correlation of 0.5. That's what it would tell me. The same information is available in R with one exception. And so this is funny to me because I developed this handout out of the one that Jonathan built, which is linked from the website. And in his version that he made several years ago, they had an extra column in here that provided the same modification index using the rescaled chi-square difference, and it's gone. So this MI right here doesn't match because this is based on the regular solution, not the robust solution. But in terms of which ones are relatively more important and what the resulting standardized parameter would be, they do match. So it's capitalizing on the same problems. But the thing is that these cheat codes will never tell you that you need a new model. They will only tell you how to fix the model that you have. And I think I need a new model. Every time that you want to add a relationship between the not the factor parts of your model, then you don't really have a single factor model anymore. What you have is forgiveness of situations and some other stuff, because there's something else that's systematic to your data, but you don't have a name for it. It's unaccounted for multidimensionality.
Is there a way to visualize this?
Certainly there is. Let me,
This one?
yes, sir.
So in this case,
Let me find a picture for you. Go ahead.
what we want to do is we want to reduce the chi-square difference in order to make both models comparable. Our model and the saturated one.
Mm-hmm.
Okay.
The idea is to resolve the specific reasons that in the aggregate make our model worse than perfect.
Okay.
So when would you add a single error covariance use? You'd have to have a justification. So this is skipping ahead a bit, Nathan, but this picture in the middle, that's what it would look like.
Okay.
So you would depict a two-headed arrow on the error parts of the variable so these items in this picture, items 5 and 6, have an extra relationship implied beyond the one that's implied by the general factor. So in terms of their predicted covariance, it would be loading times variance of the factor times loading plus error covariance, whatever that path is estimated to be. And that will perfectly fill that hole for the discrepancy between those two.
So, because I seem to be really hung up on interaction terms here for some reason, is it like interactions between error terms?
Mm-mm.
No.
It's
Okay.
just an additional relationship.
Okay.
It is a violation of local independence. Another way to say it, it's like you're putting something in the R matrix after controlling for your factor. Another way to say it, yeah, this is the R matrix and this is G, by the way. Little things like that. So yeah, I don't have a picture of it, but that's what it would look like if we did this, because I'm not going to do this, is why I don't have a picture of it. So based on the patterns that I'm seeing here, so it's the same information in different scales, paying the most attention to the normalized residuals here, I'm not going to add error covariances. I'm going to solve the problem that the positive items want to be more together than the negative items do, and just make a two-factor model. When you fit CFAs to your own data, which will happen in homework 3, I do not want you to just blindly follow my example. I want you to use the results that you have for these tables and make informed decisions as to what is a reasonable approach. So the goal in this class will never be to make it fit. That may not be possible in real data. It just may not work. What I will be looking for is that you understand this information and you can react to it. Like if you see that, these two items want to be together, but then you look at the content of the items and there's no reason that these two items should want to be together, then it would not make sense theoretically to add in an extra relationship. What often happens is items that are worded the same way, that have a common stem or have a common piece to it, want to be more together. And if that's the case, then that's a reasonable modification. But you'd have to be upfront about the fact that you added it after the fact. And it would need to be replicated in further samples. Okay. So do you want to see the two-factor model? Here it is, with some extra stuff to the code. So I am on page 14. So what I am doing is separating the items that are worded positively from the items that are worded negatively. So instead of just sit, I've got sit P and sit N. I have items 2, 4, and 6 loading on sit P, items 1, 3, and 5 loading on sit N, and then I have these things. These are labels. So the loading that goes with item 2 onto this factor is now called L1. The loading that goes with item 4 is going to be called L2, and the loading that goes with this one is going to be called L3. Now, why would I do that? To make it do math on my loadings, with my loadings. So I am setting up the idea of what I refer to as estimate statements in SAS, LinComs in Stata, general linear hypothesis tests in R. Basically, if I want it to do math on the model parameters, I label the parameters and then I can ask it to do math. Now, why would I want to do that? For instance, computing reliability. So we will talk about that as an alternative to alpha, but that's what the labels are for. Our new friend, omega, instead. So I'm labeling loadings 4 through 6 here for this one. Likewise, in brackets, do you remember what brackets are for in M+?
Variances?
Oh, that's when it's by itself.
Means?
Yep, means or intercepts. Yep. That's why it's an I for intercept. And then these ones, now say that again, Vladimir. What are these for? These are variances, yeah. And so the model knows if it's a variance or a residual variance based on everything else that's in there. And so I've just labeled these as E's. Here are my two factors. So I have the variance fixed at 1 for both. So the same rules of identification apply. Every factor in the model has to be identified. So I've chosen to fix both factor variances to 1 as my identification on the variance side. That allows me to estimate all the loadings on each factor. Likewise, I have fixed both factor means to 0 so that I can estimate all 6 intercepts. And the new piece of code is right here. Can you guess what that thing is? Feel free to read from the screen.
Factor covariance?
It is a factor covariance. So the keyword with is how you make covariances. So if you want an error covariance, it would be like item 1 with item 2. If you want a factor covariance, it's factor 1 with factor 2. So it's with. And I've labeled it as factor cov 2. So I labeled everything as a tool to sort of help describe what these actually are. But I'm only going to make it do math on the loadings and the error variances. Yes, sir?
So, since factors are based on covariance, is that the covariance of the covariance?
Nope, this is just literally how forgiving you are according to these 3 items is related to how forgiving you are on these 3 items. To the extent that this covariance is anything less than perfect, a 2-factor model will fit better than a 1-factor model. Another way of looking at it is that our previous single-factor model said that these are perfectly correlated. I'll say that again. Our previous single-factor model says that this relationship is perfect. It would be a correlation of 1. That's a single-factor model. I'm allowing it to be something less than perfect. Another question?
Well, because since factors aren't measurable, so if you're finding the covariance between 2 latent things, then what is it doing behind the scenes, if that makes sense?
Behind the scenes, it is building a predicted sigma matrix to plug into the likelihood function.
Okay.
This is your G matrix. You're allowing your random effects to be correlated. You're allowing your factors to be correlated. This is a choice that you would make to have it or not, but it makes sense to have it in most cases. So I'm going to skip that stuff for now.
Wait, I have one question.
Okay, this stuff for now is what I'm skipping. Yes.
I assume the answer is be consistent with how you're scaling your factors. And could we technically, fix the variance on one factor and the intercept on the other?
Yes,
Okay.
you can mix and match. Then it would be up to you to keep track of what a unit is, because it would vary across, but if you want to do it that way, sure.
Seems like a lot of work.
Well, so here's a situation in which you might. Let's say that one of my factors is hypothesized as a predictor, and the other is hypothesized as an outcome. And rather than have a with, I want to have a directed arrow, which an M+ would be an on. So in that case, it might be useful to have my predictor have a variance of 1, so it's like standardized, and I can think about the units as standard slopes, and then let the outcome have an estimated variance because I know it has to become some other number left over after being predicted by other stuff.
Thank you.
That would make sense. But yeah, it's totally up to you. So Levon, folks, I have the same thing applied with the labels and then an asterisk in front of each of the parameters. That's how you add labels to Levon. But otherwise, the model is exactly the same. So here are my 2 factors with their labels in front. Here are my intercepts, squiggle, label, star, 1. Here are my error variances, squiggle, squiggle, with the labels in front. Here are the factor variances, also squiggle, squiggle. Here are the factor means, single squiggle. And that's my squiggle squiggle with one thing on the end and the other thing on the other end. That's a covariance. And the rest of this is linear combinations that are going to, or nonlinear combinations in this case, that are going to form a reliability coefficient that we haven't talked about yet. So any questions on the two-factor code? Let's see how it worked. So here's all the stuff that I'm asking for in R to match all the stuff that I get out of M+. So it's nice in R you can turn pieces of output on and off as you need them. In M+, you get everything. You don't get a choice. Survey says, by the way, that is from an 80s game show, that phrase, survey says. Help me, I'm losing it. What's it from? Family Feud, yes. So the top 5 answers. Ways to get bored on a Tuesday afternoon. Ooh, survey says SEM class at 3 o'clock. Ding, 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 number 1 answer, but we're almost done. So number of free parameters in my two-factor model is 19. How many did we have before when it was only one factor?
18.
18. Why is it one more? Factor covariance. Yep, that's the only thing that differentiates this, is the idea that it's less than perfect. And here's my model height relative to the best model. So the H1 value will stay the same because it's describing the data. The HO value, remember you are the hoe, that's the one that changes. And now my chi-square tested model fit is quite different. It's down to just 25 as a test statistic on 8 degrees of freedom. And it's still significant, but like this is much, much better. And this is where I'd be like, it's only significant because I have 1,100 people. I'm going to ignore that. Let's look at the rest of them. RMSEA, what do you think?
Good.
Just barely.
It's just barely, but look, close fit. So this is a p-value testing the hypothesis of close fit rather than perfect fit, and non-significant means it is close enough to close. How about CFI and TLI? Yeah, definitely good. Better than 9.5 is like the last cutoff in terms of what people would say. And also, SRMR is only down to 0.03, so our average correlation discrepancy is only 0.03. That's really good. So yeah, I'm going to call it good based on this, but I'm going to check the local fit too. So this chi-square test tells us how much worse than perfect our model is. This one is still stupid and useless. Does anything on here that is default output tell me if my two-factor model is better than my one-factor? No, that you got to do that yourself. So comparisons of alternative HOs, such as two-factor versus one-factor, you got to do that. So I have a spreadsheet, if you're going to use M+, where you enter the model -2, or no, wrong class, model log likelihood, the scale factors, and the number of parameters, and then the rest of the part that's in the blue here is calculated for you. So the scale difference in chi-square is 341. And folks who are using R, you can use the ANOVA function. So model 1 was the single factor model, and model 4 in my code is the two-factor model, and it gives you the scaled difference in log likelihood as the 342, which is exactly what I get out of this. You may have to ask it to cough up more digits than this to work for the homework system, but you can use this to do it, and it should work. So this test statistic is telling me that I have headed in the right direction. Two factors does fit significantly better than one, and every other standard in terms of this suggests that the model is pretty good. So here's my results. First, the unstandardized solution. So all 3 of the items on each factor do appear to have significant loadings. The intercepts are going to be the same. Residual variances are going to change because they're based on a different model. Here's the standardized results. So relatively speaking, it looks like item 4 is loading a little bit higher on this positive factor, but these are all decent. And on the negative factor, it looks like 3 is the relatively best one, but these are all, I would consider these reasonable effect sizes in terms of correlations. In R, one of the nice benefits of adding the labels to your syntax is that it adds them to your output. And I really like this because if you have a giant model where you're only looking for certain things, you can label just those things and it will pop out at you like this. So I think that's a very nice feature. I wish it didn't abbreviate my labels as much, but you can't have everything. And I'm sure there's a way to fix that. I just don't know what it is. So in terms of the solution, the covariance between my factors is 0.56. How do I convert that into a correlation? Or do I need to?
They're on the same scale.
Variance time variance.
Yeah, in this model, because my factor variances are 1,
1.
this is a correlation.
Yeah.
Yet another reason to have it scaled with the z-score. So this correlation would be given in the standardized solution. So 0.56. So your tendency to forgive situations as measured by the positive items is only related 0.56 to your tendency to forgive situations as measured by the negative items. Now keep in mind that this is a positive correlation because all items have been coded such that higher values should indicate more forgiveness. But conceptually, what I would call this negative factor is more like lack of unforgiveness. So lack of unforgiveness is not the same thing as forgiveness, according to these data. In practice, do you know what people do with these items? Can you guess?
I don't know.
Nope. What do people do with the Heartland Forgiveness Scale? They add them up. I don't sanction that, by the way, but I'm not providing free statistical advice to all of the people who email me about this. No. But this is a more general idea. If whatever this is only correlated 0.5 with whatever this is, what kind of inference do you think you would have if you add it all together? Like, those are not very highly related. So you could end up with a middle score, so to speak, from adding this stuff together because you're low on one and high on another, or medium on both, or high on one and low on another. And I don't know what the result would be from putting all of that together.
Lisa?
Yeah.
Here, the estimates for each indicator, we can interpret them as the expected change in our item score. But in the case of the standardized version, that's the correlation between the factor and the indicator.
Yes.
And that's all, right?
Yes, so 1.007 is the unstandardized slope. That is how much item 2's answer will increase for every standard deviation of your factor higher. And if I take the item and put it into a z-score metric, then that increase is 0.73. Or you can say this is the correlation between the item and the factor.
Okay. So, and in this case, those values for the estimates depend on the scale you have for the indicators.
The unstandardized solution does depend on the scale, because what a unit means is governed by the scale of your factor.
Yeah.
The standardized solution will be the same, regardless of how you identify your factors, how you've scaled them.
Right.
Yep. Yes, indeed. So is this good enough? The global fit suggests that it is. Let's look at local misfit. So here are the discrepancy matrices, so residuals of the correlation. So the largest correlation in absolute value is just under 0.1 in terms of how far off it is. I can live with that. The normalized residuals are still flagging 2 of these as relatively larger. So it is still concerned about items 1 and 2, and it's concerned about items 5 and 6. I have no reason that would justify adding in those additional relationships, so I'm going to call it good. Of course, the cheat codes are like, are you sure? Because you know, I could make your chi-square go down by 10. And now there's two different kinds of suggestions in the cheat codes. There are by statements and there are with statements. By statements are equal squiggle in R, and with statements are squiggle squiggles. So by statements are cross-loadings. That means, you know what? I know that you said that situation 2 loads on the positive factor, but really it wants to load on negative also. And if I add it onto the other one, this is how much your chi-square would improve, and this would be your new loading. And also item 6, I know you put it on the positive factor, but I think it could go negative also. Your chi-square will go down by 10, and the loading would be 0.16. So these are trying to do the same thing. What they're trying to do is allow additional relationships between items on different factors. And one way to do that is to put a loading to connect it directly to the other factor, or to put error covariances in. So in this case, it's actually items on the same factor that are causing the problem. So that one doesn't even make sense based on the wording. But if you have an item that has a lot of error covariances that it wants with something on the other factor, a cross-loading can solve that problem. But I don't have any rationale that I could defend as to why I would add these things, particularly the cases where the loadings would be negative. And so I'm not going to add it, and I'm going to call it good. Yeah.
How would you interpret cross-loading in this case?
This is the extent to which item 2 is related to the negative factor. So a 1 unit increase in the negative factor would make the expected response to item 2 go down, by 0.2. It doesn't make any sense.
Yeah, because if it's negatively worded, then...
But it's been fixed.
Oh, okay.
Like everything is fixed so that up means more forgiveness.
Oh, it's a reverse time.
Mm-hmm.
Okay.
It's been fixed. So yeah, even after fixing it, the relationship that it wants me to include is negative. So I can't make that make sense. Yep. So that's why I called it good. All right. 307. How are we doing, kids?
Fine.
Are we hanging in there? Ish? Is week 6. I know. We're like over a third of the way done, though. No? Not better?
Nope.
Okay, fair enough. I will quit trying to make it better. Yeah. See if there's anything else that I want to say that isn't like a whole new thing. So yes, the full version of the R syntax and output that was made several years ago, 2017 in fact, is here from this link. To do plots and things, I didn't put that part in my program, but you can check it out. So the next thing that I did here is look at factor scores and stuff. So we have outputted factor scores for each of these things. I know what I want to do. I'm going to do this picture real quick. This is a good thing to end on. This is slide 69 of lecture 4. So this idea that there's discrepancies in what the model says with respect to how related variables are and what the data say can be addressed in multiple ways. Here's 4 different ways to solve that problem. So in this example, which is from your textbook, the Brown book, page 181 is where I stole these pictures from. There are 6 items measuring some kind of anxiety related to social interactions. And 2 of them have to do with public speaking in particular. So those sort of break off into their own thing to some extent. They have more than just social anxiety as a common thread. So one way to do that is 2 factors. That's what I just did. Another way to do that would be to keep the single factor, but let the residual errors of those 2 items have an additional relationship. Another way to do it is this thing, which is known as a bifactor model in IRT land, otherwise known as a method factor in CFA land, where I split it into 2 factors, but everything still loads on the first factor, and I have a second factor that sort of swoops in and takes this extra relationship. And then the last one is, well, I know you have 2 factors, but I still want to talk about social anxiety as one thing, So I'm going to stick this higher order construct on it that predicts those two, so I have one circle to work with. Now, what if I told you that all 4 of these fit the same? The same. They make different statements, but they're the same.
There's no way to like say this one fits better than this one.
Not if this is all that's in your model. The only way that you could get them to become different is in how these circles relate to other stuff. So here's one way to think about it. Do you want to just like fix it and have one factor? Or do you actually want to represent individual differences in public speaking as its own thing? Because just fix it relegates whatever this factor would be to this error covariance, and that error covariance cannot become a variable that predicts other stuff. Question? Or fingers? Okay. Now this one in particular, the label is misleading, I think, because these 2 items still load on social interaction anxiety. So this is not public speaking. This is whatever part of public speaking is above and beyond social anxiety.
So that would insinuate that people have social interaction anxiety, and then there's some people who have extra anxiety with public speaking?
Something else that's
Okay.
above and beyond. So like this model says, no, there's social anxiety and then there's public speaking and they're related to each other, but this is not the same factor because this is only defined by these 2 and this one's defined by all of them. Whereas over here, this factor is only defined by these 4. So in addressing, basically the common theme here is unexpected multidimensionality. There's some other relationship between these 2 items. Do you just want to bury it and stick it in an error covariance, or do you want to make it a thing and potentially have that become a predictor or an outcome relative to other stuff? The idea of making it a thing is consistent with fitting a factor of some kind. So there's a lot of choices here. In IRT models estimated with maximum likelihood, you can't have error covariances. That's not a choice. You have to do it this way. And so that's why bifactor models are much more of a thing in IRT, is because you're stuck with them. You can't have error covariances if you're using full information maximum likelihood, only if you're using limited information. WLSMV, or diagonally weighted least squares, for those of you who saw those words in your papers. So I'll just let that sit. Let that sit with you for a couple days. How's that sound? Yeah? Zoomers, is that okay with you too? We're just going to let that sit. Let it percolate in the background. No, the Zoomers are not here either. I think we're done, aren't we? Yeah, oh, no, they're like, no, I'm here. There we go. Yeah, the delayed thumbs. I understand, folks. I get that way around this time of day too, and I'm the one talking. So how about we call it a day? And I will see you on Thursday and let you know when your next homework is available, which is not yet. How's that sound?
Yep.
All right. Thank you for being here.